Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on linear programming duality. And in this lesson, we're going to learn a new fact called complementary slackness. It's a very important property of linear program, and in fact is an equivalent property to strong duality. So here is complementary slackness in form of a theorem. Let's parse through this theorem. It says, let x and y be feasible solutions to the primal and dual problems, respectively. So x is primal feasible and y is dual feasible. Here, by primal dual problems, I mean primal is minimize C transpose x, subject to ax greater than or equal to b, less than or equal to b, equal to b, and y is corresponding dual problem. So if x and y are two feasible solutions to the respective problem, then x and y are optimal solutions for these two problems respectively if and only if they satisfy the following conditions. Okay, the following two conditions can be grouped into two parts. The first part is called primal complementarity slackness condition, and it says these two solutions, x and primal solution and y's solution, should satisfy this condition here. This condition is called complementarity slackness. So what it says is the product of yi for the i's primal constraint times the primal constraint, the i's primal constraint, which is ai transpose x minus bi, should be 0. This product should be 0, is 0 for all constraints. Remember, for any primal constraint, we assign a dual variable. So we have this pair of product for every primal constraint. So in other words, that there can be only two possibilities. Either the primal constraint, i's constraint, is active at x. That means ai transpose x minus bi is 0. So in that case, the product is clearly 0. Or if this primal constraint is not active at x, then yi, the corresponding dual variable, has to be 0. Okay, so that is called primal complementary slackness. So if x and y are optimal primal and dual solutions, then they need to satisfy this. And furthermore, if x and y are primal and dual optimal solutions, they also need to satisfy the so-called dual complementarity slackness condition. So what this says is the dual of this, meaning if you look at the dual constraints, these are the dual constraints, the j's dual constraint, cj minus y transpose aj, then this dual constraint times the corresponding primal variable xj should also be 0. So again, there could be only two cases. Either this dual constraint is active at the current dual variable, in that case product is 0, or if that dual constraint is not active, then the corresponding primal variable has to be 0 if the primal and dual variables are both optimal. So this is called dual complementarity slackness conditions. And the theorem says if x, y are optimal for the primal dual, then they have to satisfy both slackness conditions. And furthermore, the converse direction is also correct, meaning if primal and dual complementary slackness conditions are satisfied at x and y, two feasible solutions to the primal and dual problems respectively, then these two feasible solutions actually are also primal and dual optimal. So this is the complementarity slackness theorem. And it turns out that this is equivalent to the strong duality, meaning if the complementarity slackness conditions hold, then the strong duality hold, and also vice versa. So we're not going to prove this, but we're going to see examples of how to use this theorem. So here is an example considering the following LP primal and dual pair. And you should really take this in this exercise. If I give you the primal LP like this, you should be able to formulate the dual LP rather quickly. And if I give you the dual LP here, you should be able to formulate the primal LP rather quickly. Okay, and as we learned earlier, that the dual of the dual is the primal. So the position of the primal dual are completely symmetric. You can call any one of these the primal, the other the corresponding dual. So if you observe that this problem, if we call this the dual problem, then this dual problem actually only has two variables. So this dual problem, we can just plot this on a piece of paper and solve this graphically. And if you do that, you can get the optimal solution to the dual problem to be y1 star equals 2 and y2 star equals 1. And the primal problem has three variables, so it's comparatively harder to solve. The question is, if we can solve the easier one, the dual problem, can we use that dual optimal solution and the relation of primal dual to figure out the primal optimal solution without actually solving the primal problem? So that's the question. And it turns out that complementarity slackness exactly gives us a way to do that. So here is the procedure. There are two complementary slackness conditions, the dual and the primal. The dual is about the product of the dual constraint and times the primal variable, so being equal to 0. So at the dual optimal solution, we should have the following. Well, this just plug in the dual optimal solution to the constraint. And if we plug in 2 and 1, x1, y1 is 2, y2 is 1 into these two constraints, we'll get 5y1 plus 3y2 equals 13, and y1 plus y2 equals 3. So 13 is equality, active. Well, the second constraint is equal to 3, which is strictly less than 10. This is inequality. So if we apply dual complementary slackness, then immediately tells us that x2 times this constraint equal to 0, and this dual constraint gives us a non-zero 3. So that means the primal x2 variable has to be 0. So that is a very useful information, that without solving the primal problem, we already figure out that the primal variable, optimal variable, has to be 0. So if we plug that back to the primal problem, x2 is 0, right? Then immediately we get x1, which is 1. And then we substitute here, we get 1 here, then x3 also has to be 1. So in that way, we have solved the primal problem without even using any simplex or directly solving the primal problem. You can do the other way around using the same example. Suppose we know the primal optimal solution is 1, 0, 1. Can we get optimal solution to the dual problem? Well, we can do the same. You can look at what is the slackness of the constraint. So primal problem has has two equality constraints. So that means the complementary slackness condition automatically holds, right? Both primal constraints are active here. But if we use a dual complementary slackness, since both x1 and x3 are non-zero, x1 and x3 are non-zero, in order to have the dual complementary slackness, we should have the dual slackness, meaning 5y1 plus 3y2 minus 13 has to be 0. And also 3y1 minus 6 has to be 0. So we have this. And that will give us y1 is 2, and then substitute will give us y2 equals 1. So in other words, we got the solution here. And then you need to double check that primal complementary slackness holds. Well, complementary slackness automatically holds because of the equality constraints in the primal problem. Therefore, we got a solution, primal solution, dual solution, which satisfy the primal and dual complementary slackness. Therefore, by the theorem, it has to be optimal. So this will demonstrate a way to how to use complementary slackness to give us useful information of primal dual optimal solution. So let's summarize. We learned complementary slackness condition as equivalent condition to certify a feasible solution xy being optimal. And we have learned how to use it to quickly solve a linear program. So this concludes our discussion on linear programming theory part. To summarize, we first learned the principle of relaxation, and we give a specific systematic way called Lagrangian relaxation, which can be applied to many optimization problems, not just LP, but we do apply it to LP to formulate the LP dual and to construct the rules that the LP dual is formulated. And then we studied weak and strong duality, the relation between the primal and dual objective value. These are very important results. And then we use that to derive the table of possibles and impossibles. Finally, we come to complementary slackness condition as an equivalent condition to strong duality and see how to use it to solve LP. So in the next module, we're going to see applications of LP duality to interesting problems. So this concludes this lesson and this module. Thank you.